Okay.
Yes, it will be great.
Okay. Good afternoon. Okay. So I have started recording, and what should we do today? Okay. So as I have said that today I'm going to talk about something about this linear algebra. Okay. So what we can do is uh, I can say that how we can represent a matrix. So for example, if I want to represent a 3 by 3 matrix, like 1, 5, 6, and 7, 4, 2, and then -3, 6, 7. So I can represent this 3 by 3 matrix like this. So there are various ways you can do. I prefer to present it like this. So for example, 1, 5, 6, and I put a gap. We can either, you can even put a comma between them as well. But even if you put comma or no comma, then it's the same. And then for the, this semicolon is shows that it is the end of the row. So the next one entry will start in the second row, and like that. Okay, so if I will hit enter, so then it will show that the matrix is 1, 5, 6, 3, 7, 4, 2, -3, 6. Even I can put, like as I have mentioned, that comma in between, comma. Let me see, I think it will also show up like this. If I put like comma over here, then it's the same. Even these spaces are not necessary if you put comma. That means you can skip these spaces. Okay. So for example, this space I can, so comma, and then I without any space. If I put without space, but I put comma, then it's the same. So, but normally what I do is I use like this, okay, with space and then semicolon and like that. Okay, so this is how you represent a 3 by 3 matrix. If I want to transpose this matrix, so for the transpose, the shortcut is you put this matrix name A and then put an apostrophe, okay, which is a key on the keyboard next to the enter key, okay, apostrophe, okay, and then hit enter, and then it will transpose the matrix. So you can see that original matrix was 1, 5, 6, 7, 4, 2. So now we can see its transpose. Okay. So next thing I want to show is that, for example, if I have 3 row matrices, for example, X row matrix, first row matrix is, by the way, I just forgot to represent another way for showing this matrix A. So for example, if I have this matrix A, like this over here, you can, sometimes if the matrix is slightly bigger, it may be easier for you to put it like this. So for example, instead of instead of putting semicolon, you can hit enter, and no, okay, let me show it again. Yeah, if for example, if you have like this, so you write the first 3 columns. You write the first three members and hit enter, and then if you will see that your cursor will go to the next one, okay, and then you can put these next 3 members, 7, 4, 2, and then hit the enter again, and then you can put 6, 2, 7, and then close the bracket. And now hit enter. After closing the bracket, it will show up the same matrix as well. So in this way, you can also put it. So maybe if I do like this, yeah, so maybe if it is like this, so then I can hit enter, and then I can put a gap like this. And you can even kind of align it over here, 7, 4, 2, and then 6, 2, 7, and then bracket close. Okay, so in this way you can also put it. So there are various ways for entering the matrices. Of course, there may be some more ways as well. Okay, so now let's do the second point for this tutorial is X. If I have a row matrix, so a row matrix I can put like this 8, 6, 9. So for example, this is a row matrix. Okay, so 8, 6, 9. And if I have a Y row matrix, minus 5, 6, 1. Okay, minus 5, 6, 1. Okay, so this is another row matrix. And if I have Z, another row matrix, 4, 8, 2, 4, 8, 2. This is another row. So now I have defined 3 row matrices, X, Y, and Z. If I want now from these 3 row matrices, if I want to combine these row matrices into one 3 by 3 matrix, so I can do it like this. So suppose I want to store this combined row matrix in a matrix named B, then I can do it like this. So I can put X. X is representing the first row matrix, and I want the second row to be Y. So I can put a semicolon, and I want the third row to be Z. I can put semicolon Z, and then I can hit enter. Yeah, so there is no need to put space over here, but for clarity, you can put a space as well. Okay, so you put a space or no space, that doesn't matter. So you can see that now we have one row matrix B69 minus 561 482. So you see 869 minus 561 482. So it has been combined into one row matrix. If you want to see without row, without a space, so it's the same result. Okay, so you put a space or no space, it doesn't matter. But a semicolon, of course, we need to provide to represent the end of the row. Okay, so with this thing in mind, let's see now. You can see that you can add these two matrices, A plus B. Okay, so we remember that what was A? A was previously here. A was here 1, and then 1 plus 8 is 9, and then so in this two matrices have been added, and their elements have been added element by element. So if A plus C is equal to A plus B, so then A is equal to C minus A. Yeah, from the matrix properties, we know that. So if we want to get A, and then we have to we have to subtract B from C. So A is equal to C minus B. So we will get back A156 742. So it is the same as over here 627. Okay, then so this was the addition and subtraction for the matrices, and for the matrices multiplication. So what we can do is we can just use A star B, A asterisk B, A asterisk B. So that will be the matrix multiplication. So we have A matrix, we have B matrix, we want to multiply them because both have 3 rows, 3 columns. So number of columns of A is equal to the number of rows of A. They are compatible. So then we will get A star B is equal to 784, 26. So this will be the matrix multiplication. On the other hand, if we want to just multiply only the corresponding elements, so then you will use the A dot star B, A dot star B. Okay, this is the dot, not comma, dot star B. So in this case, elements of the respective elements of A and B will be multiplied. So for example, in this case, A was what? 1. and 1 is multiplied by 8, that is 8, and A was 5. This 5 element will be multiplied by 6, that will be 30. So this is the element by element multiplication. Okay, so sometimes the multiplication of the vector matrices is not compatible. So for example, if I define another matrix D, which is a 2 by 3 matrix, okay? So it is 1, 4, 3, semicolon, 5, 8, 1. So this is a 2 by 3 matrix. 2 rows and 3 columns. So if I hit enter it, then I will get this matrix, okay? But now if I want to multiply A by D, okay, matrix multiplication, because A is a 3 row 3 column matrix. So A has 3 columns, but D has 2 rows only. So this multiplication is not possible. If I will try to do it, I will get this error message that the incorrect dimensions. On the other hand, D star A is possible. D star A is possible. Why? Because D has 2 columns. Sorry, D has 3 columns and A has 3 rows. Okay, and we will get 2 by 2 matrix in this case. In that case, yeah. So in this case, D star A, we will get a 2 by 3 column. So D star A is possible because D has 3 columns, A has 3 rows. So 2 by 3 matrix was obtained in D for D star A. Okay, so the a number of operations, of course, we can do. If we want to find the inverse of the matrix, so let's see, we want to represent the inverse of this A matrix as AI. For this, we can use the INV function in MATLAB. So INVA, that means it will show that we want to take the inverse of this matrix A. So we can readily get this answer as 1 minus this one, and this will be the matrix A. So this will be the inverse. But how we can we confirm that this is the inverse of this matrix? So what we can do is we can multiply A with its A inverse. Okay, and then we can see that we will get an identity matrix 1 minus 0, that is of course 0, 1 0 0 0 1 0 0 0 1. Okay, so we get an identity matrix. So A times its inverse is the identity matrix. So by the way, the identity matrix can be represented in MATLAB by I command. Okay, I command. So if I want a 2 by 2 identity matrix, so I will put I2. Okay, so that will be a 2 by 2 identity matrix. If I want a 3 by 3 identity matrix, I will put I3. I is equal to I3. So that is stored in I matrix. Okay, similarly for 4 by 4, I will get like this anyway. So lastly, I save the 3 by 3 identity matrix. This identity matrix is actually useful in many, in some cases. So for example, if for example, if I interchange the first and third row of this identity matrix, so then what I will get it. Okay, so for example, if I define a matrix P in which which is the same as the matrix I, in which I will interchange the first and the third row. So for example, so it will be 0, first row will be 0 0 1, the second row will be the same 0 1 0, and the third row will be 1, 0, 0. Okay. So in this case, I will get this matrix P in which the first and the third row of the identity matrix have been interchanged. So this is one of the property of this identity matrix is that if I multiply our original matrix A, let me see, the original matrix A was this. Okay. So now if I take like this multiplication P times A, that means I multiply this P matrix in which I have interchanged the first and third row of the identity matrix, and then I will multiply with this matrix A, and then let's see what I will get. So here you can see that the rows of A have also been interchanged, right? So 6 to 7 have come over at this place, and 156 has come over at this place. So this type of observation can be useful in the Gauss elimination method, in which you want to show that how to interchange the rows. This type of thing may be needed for doing some partial pivoting in the Gauss elimination method. Now, similarly, on the other hand, if you want to interchange the first and third columns, so what you can do is you can do A star P. Okay, that means A and then star P. So in this case, you will see that what will be the result. So you can see that if you compare it with this case, so 6 to 7 was the third row. Now it has become the first row. It was the third column. Now it has become the first column. And the first column has become the third column. So in this way, you can do the row interchange operations using the permuted identity matrix. Okay. So this is one of the observation which you can do it. Okay, and you can get the augmented matrices, as we can see that, for example, if you want to augment the matrix A with its identity matrix, so you can put it like it is an augmented matrix. AUG is equal to A and then I. So we know that A is the original matrix A and I is the identity matrix before. And if I want to put it in the augmented matrix forms, I will just put A, I. So that will be the augmented matrix. And then you can see that in your linear algebra course, we have used this augmented matrix to manually find the inverse of the matrix. So these type of operations can be used in the matrix for the matrices in MATLAB. And finally, there is a function called size. If I want to find the size of this augmented matrix, of size of this augmented matrix, that means the size, we know that it has 3 rows and 6 columns. So it will show that the size is, the answer will show as 3 and 6. Okay, the answer will be shown as 3 and 6. So it will show that if the size of this augmented matrix is 3 rows and 6 columns. However, if I want to, because it has 2 inputs, if we want to find these rows and columns in numbers as separately, so I will assign it to a row matrix NM, okay, and then I will put size augmented matrix, size of the augmented matrix. So size of the augmented matrix will be then given by in this form, N and M. So it will show that N is equal to 3 and M is equal to 3. So I will get the size in these variable names by this command. So these are some of the ways in which you can perform the operations. And do you have any questions?
No.
Okay, so
No questions.
no questions. Okay. Yeah, that was relatively easy.
Could you also provide the scripts after the lab?
For which scripts? Scripts of which?
I mean, like this lab's this document that we
Oh,
are doing
the
right
one
now.
right now I'm typing. No, I'm
Yeah.
not using any script in this one. In this, I'm just typing in the command window. So you can.
Oh no, I mean just this document, so we can like watch again and try to do it at home.
Yeah, I know. In this format, there is no document. It is.
Okay.
Yeah,
So
because
it's not like saved.
this is the command window. Okay.
Okay.
If I
So
will
command.
write the
Okay.
script
Okay.
in the editor, then there will be a document. Okay.
Oh, okay. Okay.
Okay, so we can find the determinant of the matrix A by the determinant command. Okay. So for example, if I want to, so if for A is this matrix, if I want to find its determinant, so I want to save this determinant in determinant det variable, so I can put the determinant command. So maybe I can use another d. Okay, so d is equal to determinant of A. If I want to find the determinant, so it will be minus 221. So you can find the determinant by this. And you can apply the Cramer's rule also, maybe. I don't need to show. Okay, so if you have a system of the linear equations, so for example, if A is this, okay, and the B is some matrix like 10, 3, and 2, okay, B is 10, 3, and 2, right? If you have a system of linear equations in which we have 1x1 plus 5x2 plus 6x2, 6x3 is equal to 10, 7x1 plus 4x2 plus 2x3 is equal to 3, and then like that. So we can write it like this. So first we can write the matrix A, then we can write the matrix B. And if we want to solve it for its values of x, so it's very easy in MATLAB. So we will put x is equal to A backslash B, A backslash B, and it will give us the answer. A matrix dimensions must agree. Okay, it says that matrix dimensions must agree. Yes, so can you tell me what was the mistake which I have done? Here, this is the matrix A and this is the matrix B. So matrix A is the left-hand side, the coefficients of x1, x2, and x3. And these are this is the matrix B is on the right-hand side. But when I tried x is equal to A backslash B to find the solution in terms of x, I had an error. So can you tell me what was the error?
You should have 3 rows.
Yes, yes.
Right.
So I have defined B inaccurately. Okay, so I will put B like this. So with semicolons. Okay, yeah. So now B is this. Now I will apply this x is equal to A slash B. So now I will get this solution. Okay. So this is the solution. So this solution we have got, but to verify whether the solution is correct, what I will do is I will multiply A with x, okay, and then we will get I will see whether I get the same answer. So A star x, okay, A star x, and then I will get 10, 3, and 2, so which is the same as this. So which shows that our solution is correct. Okay, if I put A star x, A star x, and I put double equal sign B, then see what happens. You will see equal sign, then what happens is 1 1 0. Okay, 1 1 0. So 1 1 0. Okay, yeah. Okay, maybe if it says that the logical array, if we get 1 1 1, that means that our equality holds true over here. Or maybe I can try, but here it shows that 0, maybe something is, maybe some truncation errors or like that. I don't know. If I put B equal A star X, yeah, 1 1 0. Anyway, maybe I just skip this point. But anyway, with this, we have checked that the solution was correct. So another way for finding the solution is like this. So let's see, our A matrix was this, B matrix was this. Okay. Another way of finding the solution is X is equal to inverse of A times B. Okay, so this is another way of finding the solution in MATLAB. X is equal to inverse of A times B. So it is minus 0.6471. So it's the same solution as we got before. Okay, so we can either use the backslash operator or the inverse. Both will give the same answer. Okay, so that was the some solution. Okay, so now let's talk about some of the script. Okay, and that will be the stuff, I think, for your assignment. In fact, in this case, I will not be developing the script over here. I have already ready-made script available with me. So I have this script named Gauss naive. Later on, I will share this script with you, okay, on Moodle. So I have this script named Gauss naive, okay, Gauss naive. So remember that there are two methods for the Gauss elimination, Gauss naive and the Gauss pivot. So in this Gauss naive, we will not do any pivoting. But in the Gauss pivot, we will do some pivoting. So this is the script for the pivoting. Okay. So if I see this script like this over here, so this script is in the form of a function. Okay. Function. So this takes the value. This function, the name of the function is Gauss naive A B. It takes two inputs, A and B. As you can you see it over here, right? So this Gauss naive function is for the solution of the simultaneous linear equations. So it takes two inputs, A and B. A is the coefficient matrix and B is the matrix from the right hand side. Okay, it takes two coefficients and then it gives you the solution, and then this is the script. So let's see how we can apply this script to find our solution. So in this, since this script is in the form of a function, so we will need to call this function. So let me just clear screen. Okay, everything clear. Okay, so now I need to call this function. The name of the function is GAUSS NAIVE. Okay, Gauss naive function, and I need to provide these values A and B. Okay. Oh, okay. So for this, I think first it will be better for me to define A. I already removed it, but anyway, I can define A. So for example, I take the same example for the Gauss naive elimination as we did in the book, which was see, I will move to the book chapter. Yeah. Yes. Here. So Gauss elimination. We'll move to the naive elimination. Naive elimination. So I use this same okay, example. Okay, 3 minus 0.1, and then I will type. So matrix A will be 3 minus 0.1 minus 0.2. Okay. So it will be yes.
Sorry, I have a question. So in the slides, it calls that one of the problems of Gauss naive and the other elimination process are the division by zero. So the only way to fix the division by zero is increasing the number of significant digits, yes? And pivoting also helps, or pivoting also
Yes.
to prevent.
In the naive Gauss elimination, there is a chance for division by zero. But for the division by zero, there is the correct fix is to do the pivoting. That means interchange the rows and like that. So pivoting can fix this problem, but increasing the number of digits will not fix it.
Okay. So it's because it will still get a zero if the
yes.
number. Okay.
Yes, definitely.
Thank you.
So A is, okay, let's define the A matrix. So 3 minus 0.1 minus 0.2, and then semicolon 0.1, 7, and minus 0.3, colon, semicolon, and 0.3, minus 0.2, and 10. Okay, so suppose this is our A matrix. So A is this. Okay, 3 minus 0.1 minus 0.2, 0.1, 7 minus 0.3, 0.3 minus 0.2, 10. Okay, and then our B matrix is 7.85 semicolon minus 19.3 semicolon 71.4 bracket close. Okay, so this is our B matrix. Okay, so now I have defined A and B matrix. Now I can apply this function Gauss naive. Okay, Gauss naive, and close it. Okay, and close it. Close this bracket. Oh, sorry. So for remember that when we call a function, the argument of the function, that means the value, the inputs of the function which you are giving have to be enclosed into the parenthesis. Okay, so I have called this function Gauss naive already, and the inputs are A and B, and A and B I have already defined previously. Okay, so it will take these values of A and B, and now we'll hit enter, and then I will get the answer. So 3 minus 2.5 and 7. And if you remember from the book, for the same example, the answer was this. So, well, I think you will say that, okay, why do we have to do this? So because I have just explained that very easy method was this. Okay, x is equal to a backslash b, right? And it will give us the same answer. But why do we have to do this? Yeah, this is a very, because when we have very easy solution available, but why do we have to do this? And actually it is giving us the same answer, and then doing this. But actually the purpose is not that. Of course, later on for solving your practical problems for your later on for your other courses or like that, you may most likely use this method, okay, in MATLAB. But here I think it is more like for your understanding. And then what because behind the scene for this backslash operator, okay, for this backslash operator, this type of algorithm, or maybe some slightly modified type of algorithm works. So if you will go through this algorithm, and then it will be easier for you to understand the mechanism behind it. So in this script, which is for a function, I will not explain it very well, but I think for your assignment, I will give you an assignment for this script. So later on I will provide this script to you on Moodle. So you will have this script, and you will modify this script to display the intermediate parts of this calculation. So that means
Okay.
when you invoke this function, so you will get the intermediate parts, intermediate matrices. So for example, like this was the example which was solved manually by the Gauss elimination. So for example, what will be in the first step, you will get this matrix. So you should get a matrix like 3, minus 0.1, minus 0.2, 0, this, and this. Okay. And in the second step, you will get this matrix. And in the third step, you will get the answer. So therefore,
So we will need
yeah,
to show each preliminary step of the forward substitution, forward elimination. Yeah?
yes. So I think I will give you an assignment in which you will be asked to modify this script to show the intermediate values.
Okay.
Of what will be the value of the augmented matrix after the first, after the second. So I think maybe somewhere you have to put the statement over here, and then you can try it. So it will be a little bit challenging for you to do it. Okay,
I
so
have a question.
yes.
So in the slides, they also talk about how we use pivoting with the scaling, and I didn't quite get the idea. If the matrix is already pivoted, should we apply scaling if it's necessary, or what? Or we should apply scaling first and then pivot?
No, I don't. The pivoting, I think, is more important. Pivoting is more important. If you do scaling without pivoting, the scaling will, I think, will just help you in some round of errors. Scaling will help
Okay.
you reduce the round of errors. But if you will do pivoting, then I don't think you will need to do any scaling. So pivoting is the most important step.
Oh, okay. So we don't need to. It's not necessary to apply scaling if we're already pivoting.
Yes.
Matrix. Okay.
Yes.
And also pivoting means that we should align with the greatest, with the biggest number from the diagonal, or just from the rows. Because
yes. So for example, if it is the first row, so the biggest number should be in the first column. If it is the second row, the biggest number in the second column. So in this case, if it is not happening, then we will need to interchange the row. And for the interchanging of the row, we know that the solution does not change.
Okay. So
Yes.
by diagonal, pivoting should be done by diagonal, yeah?
Yes.
Biggest on the diagonal. Okay, thank you.
Yep. Okay, so yeah, I think you can try different combinations. So for example, if all the elements are all the biggest elements are in the first column, then maybe pivoting may not be done, because not every kind of system can be solved. Sometimes the system becomes unstable as well. So yeah, you can try it with different combinations of different. Okay, anyway. Okay, next I want to discuss, this was the Gauss elimination, Gauss naive, and then similarly there will be the one with the pivoting as well. Okay. Yeah, so I have also the script for the Gauss pivot. Okay, so Gauss pivot will also give the same result. Okay, so for example, if I apply Gauss pivot, GSGAU pivot A comma B, so I should get the same result. So in the Gauss pivot, it's one step above Gauss naive. That Gauss pivot can handle the division by zero problem, which can happen in Gauss naive. So Gauss pivot is more efficient than Gauss naive. Okay. Okay, and then there is another one. There is another script which is called as the tridiagonal system. Tridiagonal system. Okay. For this, we have, for example, if I have a tridiagonal system like this, if I have a matrix like this, A is equal to 2.04, 1, 0, 0, and then the second column is and the second so I have, for example, 2.04 minus 1, 0, 0, and then the second row is minus 1, 2.04 minus 1, 0, and the third row is 0 minus 1, 2.04 minus 1, and the fourth row is 0, 0, 0, 0, minus 1, 2.04. So this is this system is called a tridiagonal system. Okay, you can see that this is a tridiagonal. So you can see that this is a diagonal matrix, and this is a tridiagonal because its diagonal width is width along the diagonal is 3 elements. Okay, and we have done one example regarding this in the book. So if this is the matrix A and then this is the matrix B, then matrix B is 40.8, 0.8, 0.8, 200.8. Okay, so if I have this matrix, matrix B, and then I need to put the semicolons, so to show it as an element column matrix. So it will be B. So of course, it's very easy to find the solution. X is equal to A backslash B. Okay, but just to illustrate in the tridiagonal system. So for this, we need to, I have this tridiagonal script. So this tridiagonal script is here. So it is function X is equal to tridiag EFGR. Okay, so it has it takes 4 arguments. Okay, 4 arguments E, F, G, R. E are the subdiagonal elements. That means the elements under the diagonal matrix. F are the elements along the diagonal matrix, and G are the elements above the diagonal matrix, and R are the matrices on the other side of the or on the right hand side. So in order to apply this script or the function, so we need 4 arguments, okay? E, F, G, R. So I will, based on this information, I will define E as like this. So E will be a matrix. It will be a row matrix. So you can put it as a row matrix. So these elements are -1, -1, -1. Okay.
Okay.
So these are.
No, nothing.
Okay. So these elements are -1, -1, and -1. Okay, so these elements are, so E matrices are which one? -1, -1, okay, the sub row matrices, so E. But it will, for the first row, it will be considered as 0, okay? Because in the first row, there is no actually submatrix, so we will start from 0, -1, -1, -1. Okay, we have to be, because this is a 4 by 4 matrices, so we have to provide 4 values for E. Okay, and for F are the diagonal elements. F are the diagonal elements. So these will be 2.04, 2.04, 2.04, 4 times 2.04. Okay. Here, I remember that these diagonal elements and the sub and upper elements, they don't have to be same. This is just, that means you can have different values. So for example, 2.04 minus 2, here it is -1, it will be 3.5 minus 3 minus 2. So they don't have to be different, okay? So, but in this case, we are just specially taking them as same, okay? So this will be the diagonal element, and G are the upper elements, and these upper elements are equal to -1, -1, -1, and then the last one will be 0, okay? Because 1, 1, 1, this is the third row. For the fourth row, we will take it as 0, okay? So for this script to work, and for R is equal to same. R is equal to same as which we already defined as B matrix. Okay, R is same as B. Okay. So now I will apply this function tridiag. Okay, tridiag. Tridiag, and then I will put E, F, G, R. Okay, because all the values E, F, G, R I have already defined. E, F, G, and R I have already defined. So tridiag will give me the value. So it will show that the unrecognized function or variable tridiag. Yeah, so maybe I have spelling mistake. Tridiag. So yeah, it is giving us the correction. So it is correct. So now I will see that. So here I will see that I will get this answer 65.968, 93.778. Okay, so just to check whether this answer is correct, so I will put X is equal to A over A backslash B. Yeah, so it's the same answer. It's the same answer. So again, you can see that what is the purpose for doing this tridiag over here? The purpose is just to show you that for these banded matrices, Okay, although here we have only a 4 by 4 matrix. For example, if we have a 5 by 5 matrix or 6 by 6 matrix, so in this 6 by 6 or higher order matrices, there will be many zeros over here. There will be many zeros over here. And this type of algorithm is numerically much efficient than the Gauss elimination method for these kinds of matrices. Although the answer will be the same, but the effort required by the numerically will be much less in this type of algorithm. Okay, so this was the algorithm for the tridiagonal matrix. Okay, so in which we can find the values of E, F, and G, etc. And if you remember that we found these E, F, and G coefficients using the Thomas. I think it was the method was something like called as over here. In the special matrices. Okay, it was in the special matrices for the tridiagonal systems. So it was the Thomas Lu decomposition. That is the Thomas method. Okay. So pseudocode to implement the Thomas algorithm. So that is the Thomas algorithm, which is used in this tridiagonal script over here. Okay, so we have applied the Thomas method. So next is the turn for the Cholesky's method. Okay. In fact, this and then there is this Lu decomposition as well. Yeah, Lu decomposition. So we can do the Lu decomposition in MATLAB, Lu factorization in MATLAB as well. And there is a very simple function which is called as the Lu function. Okay, so for example, let me show you over here. What was the exam? Lu decomposition chapter is here. You can take it with the help of the example. Yeah. So if we take this same example, okay, and if you want to do it as Lu, so how we can get it, okay? So let's see what is our matrix A. Matrix A is probably the same. No, now our matrix A has changed. So let me change back to this matrix. So that was the 3 minus 0.4, 0.1, minus 0.2, semicolon, 0.1, 7, minus 0.3, and then semicolon, minus 0.2, 10, and then close. So suppose this is our matrix A. Okay, maybe I made some mistake. Okay. So let me see what is the mistake. So 3 minus 0.1, 0.2, semicolon, 0.17 minus 0.3, and then it is 0.3, yeah, 0.3 minus 0.2, and then 10, yeah. So this is the matrix A. Okay, so I want to Lu decompose this matrix. So for this, there is this command Lu decomposition. So maybe I can use Lu of A, okay, and then I put it. I will get this answer, but this answer is not very useful because I want to decompose into lower and upper triangular matrices, okay? This answer is not very useful, so I don't know what is what is this showing? So I want L and U as the separate matrices. So for this, I think I will put, modify it like this. I will put L, U in brackets. That means L and U, okay, L and U, or maybe capital N and capital U, yeah, capital N and capital U. I will use the same command LU, that is the function in, LU is the function in MATLAB, and the matrix A, I will use this. I will use it like this. So in this way, it will decompose it into the L and U matrices, okay? Because in this previous command over here, it does not know what to do. So here it will provide us two answers. One is for L and the other is for U. So you can see that we have got the answer for the L and we have got the answer for U. So the L, U, okay? And we can verify it by multiplying L by U. L times U, that should be our original vector A, 3 minus 0.1 minus 0.2, and then like this, okay? We can logically verify it as well. So whether L times U is double equal to A. So we will get 1, 1, 1, 1, 1, but here I will getting something like 0, which is a little bit strange. It should be 1, 1, 1, 1, 1 actually, because 1 is for true, 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 true. But anyway, I will check later on why it is not coming as 0. But actually, it's true because we can manually see that it is L times U is equal to A. So here in this case, then this is how we can LU decompose the matrices. Okay. So again, matrix A was this. And let's see what was our matrix B is. That is the right-hand side matrix is 7.85. Same example as before, 7.85 minus 19.3 semicolon 71.4. Okay, so minus 19.3, 71.4. So this is the matrix B. So now I want to apply the algorithm for the LU decomposition. Okay, so in the for the solution of these equations in the LU decomposition, there are two steps. First step is the forward substitution to get an intermediate matrix. So let me call that intermediate matrix as D. Okay, and then that intermediate matrix is obtained by L from the lower triangular matrix, and then back substitute backslash D. Okay, so I will get an intermediate matrix D like this, and then I will use this intermediate matrix D to find the final solution. X is equal to upper triangular matrix and then backslash D, and then it will give me the answer. It will give me the answer. So the answer over here is some mistake in the answer, I think. Okay, the matrix B, no, answer may not be correct, but maybe I put the values as 7.85 minus 19.3, 71.4. Okay. And 3 minus 0.1 minus 0.2 and 0.1, 7 minus 0.3 minus 0.3 minus 0.2 and 10. Okay. So to verify whether the solution is correct, I can multiply A by X. Okay, and then see What is the answer? So the answer is 7.85 minus 19.3, 71.4. Yeah, so the answer is 7.85 minus 90.3 and 71.4. So which is the correct answer? So 7.85 minus 19.3, 71.4. Okay. But somehow the original solution which we get was 3 minus 2.49 and 7.18. I think some round off errors are coming over here due to some strange reason over here. But anyway, the solution is correct over here. So this is how you will use the LU decomposition over here in MATLAB. And finally, for today, maybe I will talk something about the Cholesky's method. Okay, Cholesky's method. Cholesky's factorization. Okay, so Cholesky's factorization was this one, if you remember. Can you tell me what was the Cholesky's method used for? For what type of matrices?
The special or dependent ones, no?
Yeah, Cholesky's method was, yeah, symmetric matrices, yes. So symmetric matrices, so yeah, here. Yeah, for this, so we did it for the symmetric matrices. So for example, is this one. Yeah, so in this case, we use this Cholesky's algorithm, which was very confusing sometimes, but it was okay. But here we have very simple function CHOL in MATLAB. Okay, so remember that in this example, we have found the coefficients for the lower matrices, that is the lower triangular matrices, okay? So the Cholesky's method. So if I define the same matrix over here for the application of the Cholesky's method, so let me define this matrix A as 6, 15, 55, 15, 55, 225, 55, 225, 979. Okay, so this was the matrix. So this is the symmetric matrix. So 6, 15, 55, 6, 15, 55, and yeah, 15 and 55, and then yeah, 220. So it is a symmetric matrix. So if I want to find its Cholesky's factorization, so what I need to do is I can take Cholesky's factorization is equal to B. And then I can apply this CHOL, Chol A. And it will give me the Cholesky factorization. Okay. So Cholesky's factorization. And then I will get this. So B is equal to Chol A. So I will get this. So here you can see that I will get the upper triangular matrix. Okay. I will get the upper triangular matrix. So if I want to get the lower triangular matrix, so then I will need to take the transpose of this. So L is equal to B transpose. L is equal to B transpose. So this will be this one. So 2.4495, 6.1237, which is the same answer as we have got over here. Okay, which is the same answer. So in order to verify it, so because the symmetric matrix, so in the symmetric matrix, then I will need to take the L times the B, okay, which is in fact the transpose of L, okay, L times L transpose. B is actually the L transpose, so we will get the same answer as original one, 6, 15, 55, and like that. So this is another, this is actually a special kind of LU factorization. So suppose if we have on the right-hand side, the coefficients are, on the right-hand side, the coefficients are 76, 295, 1259, okay? If these coefficients are this. So, and if I want to use this, the coefficients I should take in the column matrix. If the coefficients are like this, and if I want to find its solution for this system, it means this is the matrix, symmetric matrix. On the right hand side, we have this matrix B. If you want to find its solution by the LU decomposition, so now I have found the L matrix as like this. So I can find the intermediate matrix, which is equal to L backslash B. That will be the intermediate matrix. And then the final solution will be X is equal to upper matrix. Upper matrix was, so the upper matrix was X is equal to X is equal to L transpose, okay, L transpose backslash D. So the solution will be 1, 1, 1, which is correct. Okay. So because in the Cholesky's method, the LU decomposition is transpose of each other. Okay. So therefore, we have got we have used this L transpose over D. So L transpose is the upper triangular matrix. Okay. And to verify whether the solution is correct, so I can do is I can multiply A times X. So A times X, I will get this matrix B 76, 95, and 1259. Okay. So this is the application of the Cholesky's function. Right. And then one more thing is the Gauss-Seidel method. Okay. Gauss-Seidel method is more or less similar as we have done the scripts for in the case of the solution of the root finding solution. So there is this script as well, but maybe you can develop your own script for the Gauss-Seidel method, because it is kind of iterative method. And then for the iterative method, we have done a number of solutions, because it is actually the same method as it was for like the fixed point iteration method. So you can use the fixed point iteration method script for the Gauss-Seidel as well. Okay, so where was the fixed point? I don't know, maybe I shared with you. I think last class I had fixed point, something like this. I shared with you as well. Yeah. FP lab, something like this. So you can use this kind of script to develop the Gauss-Seidel method. So in this. So that's all for actually that is what I wanted to show to you today. Then so this will with this I think we have finished this linear algebra part in the MATLAB. So now I will give you a second assignment for the lab. Okay, later on. So there will be one, I think last time in the lab I mentioned that maybe I will give you the Bairstow's method script, And one of the script I will give you from this linear algebra, maybe a Gauss Pivot method, and then you will modify that script to show all the intermediate steps, and there may be one or two more questions for this lab later on.
Okay.
All right.
So could we use the function of the hold to display them? Like hold on the matrix representation, and then every time, like when the one iteration goes on, like for the for loop, it will show its present.
Yes. For because the function, the scripts which I have used, which I have shown to you, for example, this Gauss Pivot script, it is using several loops. So at the end of the loop, so you have to put something like those commands, something like this, f print f, something like this command to print it, okay, to print your intermediate results. So you have to figure out where we have to put this type of command, f print f, okay. So because this is the command f print f, which which prints the intermediate results. So we have used earlier this command into the while loop. So here we can use this inside of the for loops here we have provided. So, but first of all, you have to study these for loops carefully, and then you have to input some of the commands to modify this. Okay.
Okay.
All right. So I think this assignment will be easier to do if you have, like you and some other students, if you have followed all the previous lab examples, and then you have followed along and to practice it by yourself, then it will be easier the next lab assignment. All right. Any more questions?
Yes, also.
Oh, okay. So
About the
okay,
formula sheets.
I will upload the formula sheet. Yes. Okay.